The sky is our laboratory. At the National Center for Atmospheric Research, we actually do not forecast the weather. We get inside the weather to understand it better. We do research, we are in airplanes, we are on the ground launching balloons, deploying radars. We really try to use this as a natural laboratory to make as many measurements as possible to understand the atmosphere surrounding us. What is the atmosphere? The atmosphere is a very thin layer that surrounds the entire Earth, and it contains everything: oxygen, nitrogen, the air we breathe, and almost all of the weather: clouds, thunderstorms, tornadoes, hailstorms, hurricanes, blizzards, and rainbows. The atmosphere also carries pollen, smog, air pollution, and the greenhouse gases that cause global warming. Sometimes the atmosphere, like today, literally comes down on our head, whether it's a tornado or whether it's like low-lying clouds or a fog-like mist. The atmosphere is dynamic, it's beautiful, and it's constantly changing.
Most of us, when we think about climate, we think of the atmosphere locally and the local weather. But really, the atmosphere is a fluid surrounding all of our planet. So here at NCAR, we look at the atmosphere globally and try to understand the interaction of the various Earth systems. That includes the atmosphere, vegetation, the ice components of the Earth, the ocean, and the sun. The Earth system is so vast, we use a combination of satellites and computer models to help answer various questions that we have about the system. This involves how ice ages evolved, what's currently going on with climate, and what impacts CO2 will have on the climate system going forward. Our understanding of climate change has really evolved through the years, and we now recognize it as more than a mere warming of the system. There are changes in rainfall associated with the monsoons, the amount of tropical cyclones that we see every year, the severity of snowstorms worldwide, in addition to the frequency of droughts.
We know that changes to the landscape affect the atmosphere. For example, when we have large-scale wildfires or volcanic eruptions or dust storms, they can actually put a lot of different chemical compounds and particles into the atmosphere that can impact air quality and climate. You walk through a pine forest and you smell that pine tree smell. Those are compounds that actually go into the atmosphere and are perfectly natural. It's when they start mixing with the compounds that we emit from farms, cities, the tailpipes of our cars or our power plants. That's when you can get air quality problems, because they can mix in the presence of sunlight and form smog. It's really important, as we have changes in our air quality, that we understand not only what's happened to the atmosphere, but what's going on to the biosphere as well.
NCAR manages 2 aircraft for NSF. These aircraft basically go all over the world collecting atmospheric measurements. The C-130 can fly as close as 100 feet above the ground. You can go really slow to make very specific measurements of aerosol particles, cloud droplets, chemicals in the air, atmospheric gases. We're interested in studying the lower part of the atmosphere because that's the world that we live in. We also use meteorological balloons to complement the measurements that we do with the airplane. We use the Gulfstream 5 to go as high as 51,000 feet, and it can go up and down, collecting atmospheric measurements and do vertical profiles of these chemicals. We can actually measure pollution and how the pollution gets transported around the world.
We know a lot about big weather events such as winter storms and hurricanes that we can see coming sometimes out to a week out. But when it comes to smaller events like thunderstorms, tornadoes, hailstorms, windstorms, blizzards, forecasting those kinds of more local phenomena on a day-to-day basis, we still have a long way to go, and sometimes we only see them a few hours out in advance. So a lot of bad weather still catches people by surprise. What we're doing to try to improve those forecasts is use computer models with very fine resolution that can actually represent thunderstorms and are almost getting to the point of representing tornadoes right in the model. We take the observations of temperature, moisture, and winds from the atmosphere. We put them into the model at discrete points. Then we use the laws of physics to project those variables ahead. And what we see is actual storms developing from scratch. Where there was nothing 24 hours earlier, all of a sudden you get a big squall line developing. The research that we do helps to make forecasts better all over the world.
One of the things we study that you can't see is wind. It flows through the mountains, it flows over the mountains, around the mountains, and it's a very difficult thing to forecast. We developed wind shear technologies early on in our work here at NCAR, and those were deployed at airports around the United States. We've also developed technologies to help pilots and airlines avoid icing, turbulence, thunderstorms, and other aviation hazards. We're also working on technologies for the roadway system. We're going to be providing information to drivers about black ice, fog, high crosswinds, and hail. And we're actually going to be using the vehicles themselves as sensors to help us collect data across the whole roadway network, and then we'll merge it with traditional weather data to provide early warning information to the drivers while they're in the vehicle. High winds can be very deadly. However, high winds have a big benefit: wind energy. So we're developing technologies with the electrical utilities to help them predict where it's going to be windy and how much energy is going to be generated from the wind turbines, and then we'll use that to help them integrate wind more effectively across the nation, which is going to result in a much cleaner planet.
We depend on the sun for heat and light, but there's a lot more going on than meets the eye. The sun has an 11-year magnetic activity cycle, and what that basically means is that the sun's magnetic field is always getting churned and tangled and twisted, and every now and again it gets so tangled and twisted that it just can't take any more stress. It's almost like the sun burps. It just can't hold in the gas any longer and it just explodes into space. When that material travels towards Earth, if it just happens to be traveling in the right way, it connects with the Earth's magnetic field and hurtles down at the poles and forms what we would call the northern or the southern lights. In extreme cases, coronal mass ejections and flares dump so much energy into the Earth system, they can damage satellites. They can bring satellites down. They can damage our electrical grids and destroy the ability for us to use our cellular communications. To understand the sun, the mass and energy, and how the light that bathes the Earth comes about, you need to actually build ways of observing the sun from the ground. Here at NCAR, we build computational models and instruments that we get flown on satellites and that we put on the top of mountains.
We have models of the entire Earth system. That would include the ocean, the land surface, sea ice, and so forth. Within these models, grid boxes cover the surface of the Earth, and the vertical levels actually go from the bottom of the sea to the top of the atmosphere. Within each grid box, the calculations are performed that describe the physical and chemical properties of the system. We might have millions of grid boxes covering, say, the atmospheric component of the Earth. All of these modeling activities require very large computing resources and very large storage systems in order to handle the data. We can have as many as 100,000 processors talking to each other, interconnected by a very high-speed network. In many ways, it's analogous to the way that the neurons in your brain are connected together to form a system capable of thought. It's an unimaginable amount of computing power.
In the social science area, we're interested in how we can integrate the use of those climate models to better understand the connections between weather, climate, and health. For example, we know that weather and climate affect the life cycle of mosquitoes, how long they live, and how quickly a virus replicates. So we're looking at the potential for the mosquito that carries dengue fever to move its range to a higher elevation, potentially into Mexico City, and also to move further north in the United States in response to a changing climate.
The heat, it is relentless. It continues.
We're also working in the United States with forecasting extreme heat events, with looking at air pollution, air quality events, and also pollen counts.
High temperatures of 108. Ozone alert Tuesday.
Because the atmosphere has no boundaries, the science we do has no boundaries. We don't do science at people, we don't do science for people, we do science with people. NCAR and UCAR were created to do research that's beyond the scope of what a single university could do alone. We have over 100 universities that collaborate with us.
Okay, now I got it.
Member universities come here to develop tools, to work with other people, to bring technology back to their own country and their own institutions. And our online trainings and workshops reach school teachers, professors, graduate students, and weather forecasters all over the world. 15,000 visitors a year come to learn about science, to experience the joy of discovery, hands-on learning. The founder of this laboratory, Walter Orr Roberts, said, "It's a privilege to be allowed to do science, and in exchange for that privilege, we have a responsibility to share that science and involve people in that science." It's an incredible opportunity to study the atmosphere because it's something that connects every single one of us to each other and to every living thing on Earth.